Cool. All right. Great. So we just need to set that up. Hmm. Why? There we go. We got the here. I'm just checking what interesting articles I have collected over the weekend because I sent all these articles to myself. Oh, this one is kind of interesting. This one is about, how to understand things, which is something that I want to address in my class. Okay, so we go to participant and admit. There we go. Okay, alrighty. Can you hear me online?
Yeah.
Okay, great. Thank you. All right, so I'm just wondering how I can share this with the class. I think I can do this. I think I can do this. Oh, this is even better. I can just do that. Big link, big think, how to understand things. Okay, see if I can find it here. All right. Well, it is noontime. I'm going to get started here. So we'll go ahead and let me see. The recording has started already, so that's good. All right, so we're going to get started. First thing is not something that is related specifically to this class, but it has to do with this little article here that I kind of read over the weekend. How to understand things, which obviously is very vague and not specific. But it's basically the same article, or it promotes the same ideas that I have been trying to promote, with teaching all my classes. So if you want to read this article, all you have to do is to search for Big Think, which is the publisher, and then the name of the article is How to Understand Things. Um, which I think is increasingly important. Okay, uh, I was teaching CISP 300 this morning. You can kind of imagine the days that I have, interesting days, 300 and then 440, like the beginning class and then all the way, skipping all the way to the end of the, classes that you take here. Um, but this remains important throughout, okay? And I think this is also going to be very important, when you get out to, get a job and stuff like that, because any job that does not require understanding are not jobs for people anymore. Um, that's kind of the bottom line, unfortunately. Um, so anyway, it's just something that I think some of you may find interesting to read, and others may not go like, I don't think this is relevant to me. Okay, that's fine too. You don't have to read this. There won't be any questions about this. Okay. So now we go back to our exam one. Okay, I hope you guys all had some time to work on it, which I think is really important because people who do not work on the practice exam or the exam from last semester and just coming into the lecture code to try to understand the material, may not be getting as much out of the whole thing compared to people who spend some time, think about things, and then try to work out as many problems as possible, and then come to the class and try to kind of like, okay, there's one little bit here that I'm not quite understanding, and then just try to make that last connection. Okay. All right. So basically, just to remind people, it is next Monday. Our exam is on next Monday during the lecture. We're gonna use the entire 80 minutes on exam one. Okay, so make sure that you don't miss that day. And the number two is it is open book and open notes. Okay, you can bring any amount of dead tree based medium or media with you. Okay, but no electronics. So no tablets, no iPad, no notebook computer. All of these computers will be down by the time we take the exam. Okay, no earbuds, headphones, and stuff like that either. Um, so prepare for that. And you should be preparing for your own study guide, basically for the entire 6 weeks now, that we have been through in this semester. So make sure that you try to cover all the material. You can bring everything, including the exam from last semester, or if you so happen to find all the exams that I have ever made for this class, you can bring those too. Now, I'm not sure how much that's going to help, but sure, you can definitely bring all of that with you, okay? Because I know in some classes, professors do not like their students to bring exams from past semesters. In my classes, it wouldn't make any difference, so it's okay. It is the process of going through the exam that is important. It's not so much the exams that are important. All right, so there's that, and make sure you read the instructions carefully, okay? Because the instructions use sometimes will contain something that's relatively technical, like in the notation, for all ST in F, blah blah blah. ST is considered as a single element of the set F, and a dot dot portion, which is this portion here, is the Boolean expression to evaluate. So there are certain times, I would put clarifications of notations into the instruction itself. So make sure that you read the instructions carefully. And with that said, let me see if there are any questions before we move into the first question. Yes. Yep, it is all on paper. You may or may not have enough space on the paper exam itself, so I do encourage everybody to bring extra pieces of paper with you, just in case you need that extra paper. I will also bring some extra paper with me too, but I think it's helpful to bring, like paper that's already lined, so you don't have to kind of like to try to follow an imaginary line as you write, and make sure that you put your name on the paper, as well. Okay, so you can even pre-print. I mean, we all have access to printers these days, so you can pre-print your own paper to put your answers on for the day of the exam if that is what you want. Okay, good questions. Any other questions before we get into the exam itself from last semester? Okay, no questions. Yep, go ahead. We will try to finish all the questions, all the different parts, all the questions. Yep, that's kind of the objective of today's lecture. Okay, so with that said, let's go ahead and start here. And oh, okay, you can display my hovering, pen here. I keep forgetting to wear my half glove, so my palm does not touch the bottom part of the screen, which would start to erase things, but it's okay. I'll just be careful. All right. So the question is, they're very similar in format. Okay, so every question starts with you're given what x is, you're given what y is, and you're also given what f is. Okay, so these are all just sets. Okay, so we have to answer the following parts. The first part here is asking what is the value of, and there's an expression. If the answer is false, you'll show one tuple UV that makes the underlined expression false, okay? And you can certainly see which part is underlined. All right, so what do you think? Yes. That is correct. So we only have three elements, right? So to answer part one, okay, you don't have to show these steps, So you basically just go like, okay, if I have D and K, okay, so in that case, U is bound to D and the V is bound to K. And then you ask the question, what about the underlined portion? Is it true or is it false? What do you guys think? It is true. Okay, very good. So now we move on to the next element of F, which is CA, which means in this case, U is bound to the value of C, and then V is bound to the value of A. What is the value of the underlined expression? True. Okay. What about the last one? I think we can just kind of skip the formality and skip all the way to the answer part here. Is it true or false? True. Okay. So with a universal quantifier, everything is connected by, is it an and or or? And. Very good. So what is true and true and true? True. Okay. So that means this whole thing is true. And because the answer is true, you do not have to give me the counter example of show me a UV as an example to make the underlined expression false. Is that okay? All right. So no steps are needed to be shown here. Number two. Okay. So we're moving on to the number two here. Okay. So this is the second part. What is the value of for every ST as elements of F, for every UV as elements of F, S equals to U implies T equals V. If the answer is false, show two tuples ST and UV such that the underlined portion is false. So what do you think? Yes, it is true. Exactly. Okay, so we'll say true here. So in the second one, basically what you have is a nested loop. Okay, if you want to think of it from the control like a loop perspective. So what you have in the second question, or anything that has a nested quantifier, it is a nested loop. So basically the outer loop has to look at dk, but when the outer loop looks at dk, the inner loop has to look at dk, has to look at ca, and also jb, like so. And then the outer loop then moves on to ca. And then the inner loop has to evaluate the same three elements. So I'm just going to do the super lazy thing here because I'm using a tablet right now. So we just have to not cut for sure. We just do this and then paste like so. So that's the second iteration of the outer loop. And then for the third iteration of the outer loop has to consider the element JB. Super bad penmanship. So let me do that. Too much squiggly. So go back.
Hey, Professor.
JB. Yes.
So for question one, you know how we had like three true and our final answer was true? In that situation, if two of them are true and one is false, what would our
Hold
answer
on.
be?
Oh, okay.
Sorry.
I'm listening to the
Uh,
online question. Go ahead, please.
yeah, so for one, question number one, you know how we had like three true and then our final answer was true?
Mm-hmm.
And in that situation, what if like two of them are true and one is false? Then is
Well,
that
because
like,
I'm
mhm.
still answering the question online. Sorry. So because it's a universal quantifier, if at least one of the answer is false, then the universally quantified expression is false.
Okay, thank you.
Okay, sure. You're welcome. Go ahead. Sorry. Third time is a charm. No, it is not the same thing. So let's think about from the perspective of what does it mean when this whole expression is true, and what does it mean when the whole expression is false. So what I have done here is this portion is just showing you for question number two, how do we deal with a nested quantifier, right? Because the outer quantifier just looks at dk, ca, and jb. But for every value for the outer loop, we also have to evaluate the inner loop, which is dk, ca, and jb. So that's how we um, we have 9 cases to evaluate, basically. If at least one of the 9 cases is false, then the entire expression is going to be false. Because if any one of the 9 cases to evaluate the underlying portion is false, that means the inner for loop is going to return false. If the inner for loop is going to return false, then the outer for loop will also return false. So I can now see which one is first. Go ahead. The whole, okay, wait, okay. What do you mean by left side? If S equals U is false, the implication is true. So that's not really of much consideration to us. But we are still on question number 2. Yep, or part 2 right now. Yep. Okay, let's look at it from the flip side. Okay. What if the answer to part 2 is false? What does it mean? Okay. Okay. Well, let's look at it in a much more specific way. It means this has to be true and this has to be false, right? Because that's the only case when the implication is false. But what does that mean? It means you have found a tuple. You have found 2 tuples. They both start with the same element from the domain, but they end with different elements in the codomain. So that means one element in the domain is mapped to 2 different elements in the codomain, which in that case, f is not even a function to begin with. So this is actually checking, whether it is the case or not that f, not as a function, but only as a set of 2 tuples, is potentially mapping a single element from x to at least 2 different elements in y. Because if that happens, then f is not a function. Because one of the requirements is, in order for f to be a function, it has to be a subset of the Cartesian product between x and y, and on top of that, what? Each element of the domain maps to one and only one element in the codomain. So if you find one case where it maps to multiple elements of the codomain, or we cannot even call that a codomain. We can only say y. That means f is not even a function because it has failed that second test. Okay. All right. So shall we move on to question number 3? Are there any questions before we move on to number 3? Yes, go ahead. What do you mean one operator? Okay, yes. Uh-huh. So, well, okay. This whole thing, the underlying portion is a Boolean expression. It can either be true or false. So the quantifier is really just asking, if I were to plug in every possible u and v as elements of f into this expression, do they all return true? That's basically what it's asking. Now, this one, for the second question, it is a nested loop, but it's still asking about the same thing. It is asking, once I have fixed S and T from the outer loop, and for the inner loop, I go through every single element of F again, but this time, the first item is called U, and the second item is called V. Can this expression be evaluated to be true all the time? So we are still asking the same question, but in a nested way. Yep. All right. Any other questions for number 1 and 2, parts 1 and 2, before we move on to part 3? Yes. Okay. What did I say? Okay. And then before that, okay, before that, I think I mentioned something like, if the underlined expression, okay, let me use the mouse pointer here. If this part is false, what does it mean? It means it's not a function, but before we say it's not a function, what does that portion mean? How can you make the underlined expression here false? No, no, no. Okay. You're talking about elements, not the entire domain. Okay, but go ahead. Okay, but I'm asking how can I make the implication false? So to make the implication false in this specific case, you need okay, my glasses is cannot read long distance. You need S to be the same as U, but you need T to be different from V. So that means you would be able to find one element in F, another element in F, where the first item of the two tuples are the same, but the second item of the two tuples are different. So that means for one element in X, it is corresponding to two different elements in Y, which makes F not a function. Okay, so that's kind of why the second part two is important for that reason. Okay. And please do not try to memorize these equations to try to equate it to what you need to understand about functions, surjection and injection and bijection, because by the time you get to your exam one, I would have found a different way to express similar things. So memorizing is probably going to hurt more than it helps. Understanding how this works is going to be useful, but memorization is not going to be helpful. Is that okay? All right. So let's move on to the third one. Okay, so this is the third one, and I'm asking, is it true or not, okay, that for each element E of X, there exists an element UV in F such that E equals to U? Okay, so we'll go for the two-tier type of answers again. The first one is it true or is it false for question number one? And so if it is false, show me an example of E where it makes the underlined portion false. So what element E would you choose? If you cannot find an E to make it false, that means it is by default true. Because in this case, I'm looking for a quote unquote counter example that makes the entire quantified expression false. If you cannot find a counter example, it means it's true. Well, let's go ahead and read it. Okay. The nice thing about me not having a really good memory is I cannot even remember what I was asking when I created the question. So I'm working on the question as you guys are working on the question. So I'm not telling you something that I have just memorized over the years. Okay. So let's see what this is asking. For every element in X, there is at least one element in F where the first item of the two tuple is the same as said element E from the domain. So what is that asking? Exactly. It is asking, is every element in X mapped by function, by not necessarily function, okay, but by the F. If question number two is asking, is one thing in X potentially mapping to two or more things in Y? This one is asking, is every element in X at least mapped to one thing in Y? That's what it's asking. So what would be the answer to this question? It is true again. Very good. So the most important part about answering these questions is, okay, first of all, is the definition. Okay, how do we read the quantified expression? Okay, understanding what the symbols mean is really important. For all, there exists element of implication, conjunction. So understanding the symbols would be the first thing to do. Okay. The second thing is to read the whole thing, understanding the structure. So when we have nested quantifiers, like in question number two, and also part two and part four, then you have to understand, how the nesting itself is going to work. But even more importantly, All of these are related to the concept of functions, whether something is a function or not, whether the function, if it is a function, is it injective, if it is a function, is it surjective, and so on. Okay, so it's important to draw that connection between all of those concepts. But everything starts with the definition of the symbols. Okay, what does each operator mean? Um, that would be the first, that would be the starting point. Yep. Okay, so I will answer that question with another question, which is not atypical of me. Many of you are annoyed by that tendency of myself, yes, but that's okay. All right, so what I would do is I'm going to go to the function um, module over here. Okay, make sure I open it up. And I go to what make a function function. So you look at the conclusion here. So this part here, the entire discussion is related to what I have just mentioned, because in here we have an equal to, but equal to can also be seen as greater than or equal to 1 and less than or equal to 1, right? Between part 2 and part 3, one answers the question of whether this cardinality is greater than or equal to 1, then the other one answers the question of whether the cardinality is less than or equal to 1. Okay, so that's the association that you need to make in your head to relate everything back to the definition of what makes a function a function. Is that okay? So I'm already giving you the clue, okay? Between parts 2 and 3, one relates to less than or equal to 1, the other one relates to greater than or equal to 1, but using the same cardinality here. So the question is, which one is which one? So you have to think about that a little bit, okay? Because I think, the more you think about it, the more you're absorbing the material, because you need to make that connection in your head. All right, shall we move on to number 4? Okay, so number 4, it doesn't hurt to really kind of spell spell out, in English words, okay? To some people that helps. To me, it does not help, okay? Because I would much rather read the symbolic form because it's more concise and more precise as well. So, but if you want to spell it out, okay, this is asking for every element ST in F and for every element UV in F. Now, these two can be the same, okay? Because just like what I have demonstrated at the top here, you basically make every element mapped, or match every other element when you're looking. So there are 9 cases to consider, just like in part 2. There are 9 cases to consider. The underlined portion of part 4 is asking kind of the opposite, but not so much the opposite of S does not equal to U implies T does not equal to V. Okay, so what is the answer? The answer would be false in this case, and if it is false, we need to provide an example, okay, where you need to tell me what ST can be and what UV can be that causes the, I have no idea what I just did. Mm, so go back, back, back. Okay, maybe if I refresh the screen, it's gonna save it. Okay, so we'll see. Nope, that did not say do a single thing. I have really no idea what I did. Come on. That is interesting. Page forward, page back, still the same. That is interesting. Okay. I apologize for whatever that I did that drew all these horizontal lines. They're definitely structural in a certain way, but I cannot tell why, how I did that. Okay. Okay. So we need to find examples of ST. Okay. So we can now say if ST is, let's see, we have, wait, it is true. So I don't have to answer this part. Never mind. It is true. Okay. S does not equal to U implies T does not equal to V is true for all 9 cases. Yes. The quantified expression is true. Yep. This entire quantified expression is true. It is not false. Right here. Yeah. Which makes the implication okay. So that's fine, right? What if you match DK and CA? Is true again. What if you match DK with JB? Yep, exactly. So you just repeat that whole thing 9 times, and for every single case, it is true. Mm-hmm. Oh, are you sure you this is question one? The 5 questions are slightly different. Well, okay, if it's the same question that you emailed me, then it is a different question because I remember that was I think question number 5, if I remember correctly. But this is question number 1. Yep, that is correct. Yep, yep. No, unfortunately, you cannot use De Morgan's law because implication does not work the same way. Yeah, and go ahead. Say again. Okay, so if both S and T are D, oh, excuse me, if both S and U are D, then S does not equal to U is false. So we don't even care about the right-hand side of the implication. The implication has to be true. Yep. So are we good with number 4? Why it is true? Okay. How does that relate to the discussion of functions? Yep, exactly. It tells us whether the function f, assuming f is a function, it tells us whether f is injective or not. Okay. In fact, I think something almost exactly like this was used in the notes to describe injection, or at least I specify that in class. Okay, you guys are looking at me go like, no, I don't think you said anything like that, but I distinctly remember something like that. So we'll go ahead and find out. This is just about functions, so it's not in this module. It is the other one. Do, 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 do. All right, well, I guess I did not, do it in, oh, wait, it's almost the same thing here. That's basically the same thing because f of p is the second item of a 2-tuple. F of q is the second item of a 2-tuple where the first item is q. Is that okay? So essentially, this notation here is the same as the notation that's mentioned in number 4. Except one uses the application of f, the other one just look at everything from the perspective of tuples. Are we good so far? All right, okay. Moving on to number 5. What is the value of there exists E in Y such that for every element UV in F, E does not equal to V? Okay, so what is that asking? This can also be seen as a nested loop. The inner loop is going through every element of F. where U is the first element and V is the second element of the two tuple. And in the outer loop, it's going through every element of Y. Okay. Yes, go ahead. Yep. But to be more concise, what is it really asking? I'm asking, is there at least one thing in Y such that nothing, such that let me see here. Let me double check. For every UV in F, E does not equal to V. So nothing is mapping to E, basically, is asking. It's asking whether it is not surjective. So if the answer comes out to be true, then it is not surjective. If the answer comes back as false, then it is surjective. So what about in this specific case? With the F that is currently defined here, is it true or false? It is false. Okay, so we put the answer here. It is false. And if the answer is true, show the values of E, blah, blah, blah. But since the answer is false, there's no additional steps that we need to perform here. Because the answer is false, meaning that it is not true that there's at least one element in the codomain where nothing maps to it, which means every element in the codomain is mapped to, and as a result, the function is surjective. All right. So making those relating the notation to the concept of a function and also injection versus surjection and bijection is important, okay? Because then we can try to answer number 6. So number 6 is asking what is okay, so what is this expression? F is a function that uses X as a domain and it maps to Y as a codomain. Is that true or not? Yep. Okay, so this part is true. Okay. And then it has two subparts. Okay. If X is a function mapping X, excuse me, if F is a function mapping X as a domain to Y as a codomain is true, quote which previous part or parts of your answer led to this conclusion. Okay, so let's go back to the previous one. Okay, so question 1 is asking whether it's a subset, so it's related. Okay, so we definitely need 1. What else? What about question number 2? What about part 2? What is it asking? Nope, 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 nope. Okay, it has nothing to do with uniqueness. It has to do with, can we find an element in X that maps to two different things in Y? Because if that is true, then it is not a function. So if the quantified expression is true, then it meets another requirement of a function. It is not a sufficient condition for F to be a function, but it's a necessary condition for F to be a function. So we know 2 is a part of it. Okay. What about 3? Part 3. So what does part 3 check? It checks to see if every element is mapping to at least one thing in the codomain. So that is also a requirement to be a function. It is another necessary condition for F to be a function, not sufficient, but necessary. So we'll say 1, 2, and 3 are both, they're all needed. What about number 4? Part 4. What does part 4 check? It is checking to see if it is injective, but that's not a requirement to be a function. Okay, so part 4 does not relate to whether F is a function or not. What about part 5? Part 5 has to do with surjectiveness, which also does not have anything to do with whether F is a function or not. So it is also not related to whether F is a function or not. So 1, 2, and 3 are the only answers here. And then we have subpart 1, which is asking, is F injective, and which previous part or parts of your answer led to this conclusion? Okay, we just mentioned it, right? but I cannot remember which part again. That's how short-term my short-term memory is. It's like it just poof, evaporates. So now I have to reevaluate number four. Number four is injection. Number five is rejection. Okay, so four and five. Okay. So this would be, so first of all, is it injective in this case? Yes. Okay, so it's true. Okay, so we say true, and then we say part four is why we know. And what about number 6.1.2? It is surjective. It is surjective. So it is true that F is surjective, and part five is how we know it. Exactly. Because if part five is true, okay, so let's look at part five again. If part five is true, that means for every way I choose E, and for every UV here, E does not equal to V is true, which means E is not mapped to at all by function F, which means it is not surjective. So part five relates to surjectiveness, but in only the sense that if the answer to part five is false, that F is surjective. All right, so now we get to the last one, which is 6.2. If F is a function mapping from X as a domain, oh, okay, since it is true to begin with, we don't have to answer 6.2 because it's exclusive. 6.1 versus 6.2 are exclusive. Yes, because it has to weigh the same as part one. Well, but these two parts need to have exactly the same weight because if I give you an F that is not even a function, then you have to answer this part. Yeah, yep, 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 go ahead. Well, okay, what do you think? Read the question carefully because your part 6.1 is already saying if f is a function mapping x to y is true. So it already has its own guard condition. So by the time we get to 6.1.1 and also 6.1.2, we already know that f is a function. Yep. We don't have to say it only asks you quote which previous parts of your question led to this conclusion. You can say part five is false. Okay, that's more complete. But I'm just asking which part gives you the clue that it is surjective. Yep. All right. So are there any questions about the format of the questions? All right. So are we ready to move on to the second question? Yes. Say that one more time. Mm-hmm. Mm, possibly. But I think it's fairly clear that which previous part or parts, right? I mean, so that's it cannot be referring to the same part of this question, of this part of the question. No future references, right? All right. Shall we move on to number two? All right. So number two is kind of the same thing. Okay, so I think we can simplify the explanation a little bit, in this case. So this time we are asking what is the value of for every uv in f, u is in x and v is in y. So we just have to double check in the case of bh, b is in x, what h is from y, so that's all good. A, B looks good. J looks good. B, J also looks good. So the answer is true here. And then for the second part, okay, we are asking, can I have the same thing mapped to two different things? And the answer is actually false in this case. And then we have to show the example. So now we have to say this is false. And if you want to show just the two examples, it's BHBJ. Okay, so BHBJ. So that makes the underlined portion false, because when ST is BH and UV is BJ, then S equals U is true, but T equals V is false, which makes the implication itself false. And then that returns false for the nested universal quantifier. But when that is false, that also makes the outer universal quantifier false. So, but you don't have to explain all that much here, because the question is really just asking, if it is false, tell me how you make it false. All right. So now we move on to number 3. Okay, number 3 is asking, is everything in the codomain, is there anything in the codomain not mapped to? So we look at JBH, okay? J is mapped to, B is mapped to, and H is also mapped to. So the answer to this question is false, okay? And wait, it is actually true. Never mind. Yeah, it is true. I take it back. There we go. Part 4 is so I cannot really say this is about injectiveness anymore, because right now we know f is not a function, but the question does not say anything about whether it is injective or not. All it is asking is the quantified expression true or not? That's all it's asking. So you still have to answer that question, even if you know that f is not a function. So now the question is, can I find a case where there are two elements in um, f where they map two different things from x to the same thing in y? Basically, that's what it's asking. Okay, so let's check. Yes, indeed. Okay, because JJ and BJ, they both map to J from two different elements from X. So we still answer false for that particular part of the question. So this is still false. And then we have to quote why it is the case. So now we have to say JJ and BJ is the reason. Is that okay? All right. So now we move on to part 5. Part 5 is asking, for every element in Y, uh, is the negation. Oh, wait. Okay, I think I just wait. Okay, never mind. Okay, brain fart. Okay, so for everything in Y, um, is at least one thing in Y that is not mapped to at all. Okay, so F does not even have to be a function. So we look at that. J is mapped to, B is mapped to, and H is mapped to as well. So that means the answer to part 5 is false. All right, so we move on to 6, which is now a rather simple question, because we just say, this is false. And if f is not a function mapping from x as a domain to y as a codomain, quote which previous parts of your answer led to this conclusion. All right, so what do you think? Number 2 is, yep, number 2 being false is definitely one reason. Any other reason? One is true is fine. That's not a problem. because in this case, we want to know why it is not a function. So we just say, part two in this case. Part two alone is already enough because we need because part two is a necessary condition to make function f, to make the set f a function. So not meeting at least one necessary condition is automatically failing the whole thing. So that's already sufficient. The question did not quote all the parts that can contribute to this not being a function. Yep. That is correct, at least the way the question is phrased. Yep. Now, if the question says quote every part that contributes to f not being a function, then you have to quote both parts. But if it's only formatted this way, in which previous part led to this conclusion, then you can quote just one part because everything is ended together. So that means if one part is already showing that f is not a function, we don't have to check the rest. Yes. Okay, I cannot hear you. Sorry. No. For number four and number which again? Part four, part two, and part four. I don't think they asked the same question. So part two is nope, they cannot be the same because one is checking whether the same thing in X is mapping to two different things in the codomain. The other one is asking, are there two things from the domain mapping to the same thing in the codomain? So they're different questions. Yep. Alrighty. Number three. So this is getting faster because the more we are used to this kind of format, the quicker we can go through. Yep. Uh-huh. Okay. Okay. So if it is true, then you have to show me what E in Y meets this requirement. So which E are you using? Okay, so let's say you're using E equals to J. So now we are asking if E equals to J, then we want nothing to map to J. And in this case, we got two things mapping to J. But this is not equal to. So that means we're looking for something in Y where nothing in F is mapping to it. Okay, let me double check. We cannot find anything like that, and that's why the answer is false. Okay, let's plug it in. Okay, let's plug it in. Okay, so let's think of all the cases where E can be. So E can be J. So when E equals to J, can I say nothing or everything do not map to J? Ah, okay, this maps to J. So I cannot say everything does not map to J. Okay, yep. So it has to do with how we read the quantified expression. All right, yep. Mm-hmm. No, because I can always throw a curveball and include a two tuple where at least one part of the two tuple is not from either set. Yep. It depends on how I construct the set F. Yep. If I were you, I would not make that assumption. So far that assumption has been holding true for the first two questions, but I wouldn't make that assumption at all. Exactly. Yep. Yep. In other words, if I include like 1, 2 as a two tuple in F, then 1 would be false, right? No, we are not assuming anything. J comma J is just a two tuple. It just so happens that J is an element of X and J is also an element of Y. So there's no automatic assumption, regarding what element is where. It is just, I just give you a random set X, a random set Y, and also a quote unquote random set of two tuples that may or may not only consist of elements from the Cartesian product between X and Y. Yep. Go ahead. It is the same value, yes. So this J here is the same as this J here, but one is in set X, the other one is in set Y. And inside the tuple, inside a two tuple, position matters. The first one, is it depends on what the question is asking, right? Because in say if we're looking at question number two, this S is the first element of a two tuple, which corresponds to this S here. This U is also corresponding to the first item in the two tuple, which corresponds to this U here. So everything is positional when you're looking at inside a tuple. Mhm. Yep. Okay, so it is still a nested loop, except if you are looking at part five, you're saying, the outer loop looks at E equals to um, J, E equals to B, and E equals to H, right? And then inside, then you have, the UV matching every element in U. So UV is matching BH, is matching AB, matching JJ, and also matching BJ. And then just repeat for every single iteration of the outer loop. So basically you have a nested loop. The nested loop itself is looking for conjunction. The outer loop is looking for disjunction because the existential quantifier is an OR. We still doing okay so far? All right. Now, this is just a suggestion. I have not tried it. You can upload this particular exam to ChatGPT and ask, ChatGPT, what variation of this exam can my professor come up with, based on these particular questions. I'm kind of eager to know, whether it can model the way that I think, because that would be pretty awesome and awful and scary all at the same time. I don't think you can do it, okay? Because I think the way that I think is not very easy for ChatGPT to model. Huh? Yeah. Yeah. So you can provide that extra context and see what happens, right? So I think that's a good experiment to do with AI, is to basically give it some examples, and now that you understand the context of which part of the question is related to which other part about functions and about injectiveness or surjectiveness, you can then see if your ChatGPT can infer and go like, oh, okay, I can think of some variations of these questions that your professor may come up with for this particular exam. Yes. Similar what? Mm, well, I don't know exactly how to put it. Okay. Yeah. Yep. Hmm. All right. So question number three, we're gonna go a little bit faster this time. So we look for C is in X, G is in X, and K is also in X. H is in Y, G is also in Y. Okay, so the answer to the first question is true. The second part is one thing mapped to two different things in the codomain? The answer is no, but that means that the answer to this question is true because it is saying, we cannot find a case that one thing maps to, it is not true that we cannot find something that maps to two from the domain maps to two different things in the codomain. So the answer to that question is true. Let me double check. Yep. Huh? No, you cannot have two domains. You can only have one domain being considered. What? Question number two is asking whether this implication is always true. So this implication is picking, it's asking, okay, let's look at when this is false, right? It is false only if you can find S and U being the same, but T and V being different, which means it is false, which means this entire quantified expression is false if and only if at least one element in X maps to two different things in Y. But because that is the only time it is false, this one is fine. Okay, we don't see a single case where C maps to two different things. We don't see a case where G maps to two different things. We don't see a case where K maps to two different things. So the answer to part two is going to be true. All right, for part three is asking for everything in the domain, is there at least one thing in the function, starting with it, okay, mapping it to something else? The answer is also true. And then part four is asking if f is a function, is it surjective? In other words, we cannot have two things mapped to the same thing in the codomain. C and G both map to H, so the answer to this one is false. And then we have to quote the example, which is CH and GH. There we go. Part five. Part five is asking for everything in Y. Um, can we say that nothing in F maps to that something in Y? So we look at D, okay, nothing maps to D in Y, so the answer is true. And to make that true, the value of E is just going to be D as an element of Y. Are we still doing okay so far? So I'm just kind of fast tracking a little bit because we kind of know what the questions are asking now. All right, so getting on to number six. So number six is, we have to go for 6.1 because we know x is a function. So now we have to answer, which parts led to this conclusion. Okay, one, two, and three. And then is f injective? Okay, f is not injective, but how do we know it is not injective? It is question number four or part four. So the answer is false. Part four is the reason, and part four is false in this case, and that's why. And then for part 6.2, 6.1.2, the answer is it is also not surjective, and this has to do with part five, and part five is actually, let me go back, is true, okay, because it's actually back here too. All right, so that's for question number three. If you're getting bored, that's actually a good sign because that means you're getting the material. Your understanding is like, oh, okay, we're trying to evaluate the same kind of stuff, just on a different test case, right? So now we look at number four. Okay, so we just look at all the things here. B is in X, A is in X. Aha, G is not in X. So now we got a false here, and then we have to quote the one that does not work, and that would be which one again? GD. Yep. What do you mean each test case? For which part? Okay, let me ask you. For which part? That's going to take a long time. Write your own program to do it. Okay, do you know how to write a program to evaluate the same stuff? Okay, every time you have a lyrics list, you have a for loop where the ongoing answer is ORed to the answer of each iteration. Every time you have a for all, you have a for loop again, but every iteration is going to be ended with the ongoing answer. Okay, that's about it. Okay, then the next question is how do you nest the loop? So we can do that maybe after class, but not during class because otherwise it'll take too long. Okay, part two. Okay, so for part two, we still have to answer the question, even though we know f is not um, a function. So we just look at f here and go like, is one thing mapping to two different things? That's basically what it's asking. It does not even care whether it's in x versus in y. So we look at this, b goes to a goes to g, g goes to z. So we cannot uh, so this is true, okay? And then for 3, we are asking for everything in X, there's something in F to map it to something in potentially, okay? The answer is actually true. Okay, so I'm going to pause here because I know someone's going to look at this and go like, ah, that cannot be the case, right? What about G then? Well, G is not even in X, so we don't even consider that. That's not part of the consideration. The filtering of E is in X to begin with. That means that we don't even consider when E equals to G. Okay, that is not one of our consideration. All right. So moving on to 4. Okay, so 4 typically is asking whether the function is injective. F is not even a function, but we can still evaluate the question on part 4 because part 4 does not mention anything about X or Y. Okay, the set X or the set Y is not mentioned at all. So all it wants is to see if um, whether two different things always map to two different things. That's what it's asking. Okay, the answer is true. Okay, because every two tuple has a different second part. Okay, so that tells me it is true here. And then part 5 is asking whether there's something in Y that is not mapped to. Let's see. D is mapped to, G is mapped to, A is mapped to. So the answer is going to be, this one tricks me up a little bit too. So I have the answer. So the answer is going to be false. Yep, we cannot find something that is not mapped to at all. So it's a false. All right, but part 6 is super easy because now we know it is false. So that means we have to give it one reason why it is not a function. Part 1 is good enough. Part 1 is false. That's enough because part 1, 2, and 3 are all necessary conditions. So if it misses one of the 3 conditions, it's automatically not a function. And since the question did not say, answer with all the parts that can contribute to f not being a function, so answering just with one part is already sufficient. All right, this is 5. And let's go work on this one. All right. So the first one is asking Is it a subset of the Cartesian product? Basically, that's what it's asking. So B, J, C are from X. Okay, very good. D, J are both from Y. So the answer is true here. The second part asks, make sure that we don't have one thing for every element in the domain, it maps to one and only one thing in the codomain. That's what it's asking. No, let me take that back. Okay, I misspoke. Part two is asking for every element in the domain or in X, or for every first item in the tuple. Um, does it map to at the most one thing in the codomain? That's better. Okay, at most means it can be zero. But when I said one and only one, it cannot be zero. So I have to correct myself. Yes, I do hair splitting even on things that I said, particularly on things that I said. Okay, yes. So we just have to double check, right? B maps to D. Okay, that's good. B does not map to anything else. J maps to J, but not anything else. C maps to J, but not anything else. So we are good here. It is true. Part three is asking for everything in X, does it map to at least one thing? Which means if it maps to two or more things, it will still be returning true over here. So now we ask, is C mapped to something? Yes. Is B mapped to something? Yes. Does J map to something? Yes. Okay, so it will be true here as well. And then four is asking, are we sure that two different things in X always map to two different things in Y? The answer is no. And the example you have to give me would be JJ and CJ in this case. And then five is asking, can I find something in Y that no one maps to? So J is mapped to twice, D is mapped to once. So the answer is false to this question because I cannot find anything in Y that is not mapped to at all by F. So now moving on to part six. What is it is true. Okay, so we just have the answer one, two, and three again. And is it injective? It is for part four. It is not injective. Part four is false. Is it surjective? It is surjective. Okay, so it is true because part five is true. So sometimes I throw, not necessarily intentionally, but this is kind of like a curveball, where we confirm one thing because the answer to the other one is false. So go ahead. Uh-huh. Yep. Part four. Yep. If S does equal to U, then yes, the inequality will be false. But what happens to the overall operator? Yes, but this is universally quantified, meaning that if you find one case to be true, that's not enough to conclude for everything it is true. That's how the universal quantifier is a big and, which means everything has to be true in order for the quantified expression to be true. That's kind of what we did. Yep. Yep. Oh, that is. Uh, yep, there we go. Thank you. All right. So is there another part? Yep, there's part 6. Okay, well, we have enough time to do this, but I won't have enough time to go over the Aleph null thing, so we can do that on Wednesday. All right, so for this one, let's see. J is good, C is good, H is good, A is good. Okay, so this is true. This is also true. And for this one, it is false. Okay, because when E equals to when E equals to G, then it doesn't work because G does not map to anything using F. And then for 4, it is true. For 5, it is false. And then when we go to number 6, we say it is false, and then just quote a reason why it is not a function. I think having number 3 is the only reason we can quote in this case. So part 3 is false. And that's it for number 6. Yep, that's number 7. Surprise. Yes, go ahead. Let me see. So 5 is asking for everything in Y. Oh, you're right. Okay, I take it back. Yep. So if it is true, then we have to say which one is not mapped to, and it's B. Okay, thank you. That is correct. A, H, so B. There we go. Thank you. All right, number 7, last one, hopefully. Yep, it is the last one. Okay. All right, so we look at C is good it's from X, D is also from X, H is also from X, and then let's look at G is from Y, J is from Y, but K is not from Y. Okay, so this is false. And the reason why is because HK is not in the Cartesian product between X, Y. All right, number 2. Number 2 is still good. Number 3 is HDC. Okay, it is good. Number 4 is good. Number 5 is actually false. Yep, because they're all mapped to. And then number 6 is super easy to answer because part 1 is false. And there we go. And I still have 5 minutes left. Yes, number 6. Okay. And which part? Right. Yep. hmm no, I said, if you can find all the previous exams, you're welcome to bring them all to the exam. It was a conditional statement itself, which means if the first part is false, the conditional statement is automatically true. Yes. Number 1 is asking, is F a subset of the Cartesian product of X and Y? Subset of. F is a subset of. I can give you F that is empty. It will still make part 1 true. Mm, at most 1Y. It can be 0, but at the most 1. Yes. So it asks for every element in X, does it map to at least, does F have at least one entry mapping every element of X? That's what it's asking. It is at least one because of the existential quantifier. So it's only, we need to find at least one, right? So four is asking, looking at ST as an element of F, looking at UV as an element of F for every way that you can arrange ST and UV, S being different from U. In other words, two different elements of X, do we guarantee that they map to two different things in Y? That's what it's asking. So looking at all the elements of F, if you have two different elements in X, do they guarantee to map to two different things in Y? Injectiveness. Uniqueness is kind of ambiguous, okay? Because you always have unique elements in F, because that's how we define a set, is you cannot have duplicate elements in a set. So when you say uniqueness, what you really meant is injectiveness, which means every element of X maps to a unique element in Y, which also means if two different things in X cannot map to the same thing in Y. Using F, right? And we don't even care about whether the first element of the two tuple is from X or not. All right. All right. So on Wednesday, we're going to go through the Cantor's pairing function thing, from a different exam, because depending on the scheduling of the topics, sometimes I was able to cover Cantor's pairing function, and other times I could not. So last semester I could not, and then the semester before I was able to cover Cantor's pairing function. So that's why I sent you a different first exam that includes a question on Cantor's pairing function, otherwise known as function G of the Aleph No module. Okay. All right. So we'll work on that one on Wednesday. And I do have some free time right now, so in case anyone wants to visit me in my office, I will be in my office. I think it's the same as what we work on. It's not?
It's working. Oh, hello? Hello, can you hear me?
I just
Hello?
my internet connection is unstable. Well, actually, there's
I,
no
I could
internet
hear
connection
you
because I just
earlier.
disconnected the whole thing. Give me a second here. Just wanted to stop the recording. I think it stopped automatically, so we good. Yep. Yeah, I was just gonna see if you knew about it because it's kind of like a way of proving that a set is uncountably infinite. But the way that it works is, well, the original proof is it takes a set of binary digits and it just maps every element of that set to an element of the set of all integers, basically, or like any like countably infinite set. Okay. And then by going through each element mapped in the original set and changing the binary digit of, it's kind of hard to explain it. Okay, you can send me a link. Hold on, is it okay if I draw something on the whiteboard? It shouldn't take that long. Okay, go ahead. Okay. And while you're drawing that, I can try to answer.
Mine was on a specific problem.
Okay,
So for number 6, I have it on paper so you can see it.
okay.
Um, I'm still like puzzled by this implication thing because
Mm-hmm.
when we get one case where we got JH, which is we only got two elements in the function, right? And we match that with itself, everything's true, right? S equals U, and then we negate that, it's one, making the whole statement true, right? Which is
Wait, why would they make the whole statement true?
because one or
What,
anything.
okay. But if this side is a one, it doesn't mean the whole implication is true.
Well, so the left side was one, then we know under the hood it's one or the right side, which
No,
is
no, because we negate the left-hand side first.
you're right. Yeah, so it's negative one, which is zero, or t equals b, and so we know that t does equal b for the right side because h equals h, making it true. Because this is one, and we don't negate that.
If you have both of these elements in F, then this is going to be false. Because J equals J makes this true.
Yeah.
But H,
H
this
equals h.
is H and H.
Yeah, because I matched it with itself because I'm doing.
Oh, okay.
Yeah.
Yeah,
this
so
is
in
true.
that case, yes, that will make this true.
And then when we do the second case where we got CA, we know it's going to be the same as J and H, which is the same thing where it's true. But then when we do JH, like CA with JH, then we know it's false
Well,
because J doesn't equal C.
J does not equal to C, which means the left-hand side is false, which means the
Yeah.
implication is true.
Okay, so you only get your answer when you test all cases, right? That's
Yeah.
the best way to do it.
Yep.
Okay.
Yep.
'Cause, yeah, for some reason I was like, yeah, because J does not equal H, making it true. But in some cases, you know how when we got false, you just made the whole thing false.
Yeah.
Why is that different than this situation?
Okay, I cannot see how you can make it false. I
Well-
cannot see how you can make the implication false.
Well, for this problem here,
For which part? Because there are 7 different questions and they're all
Yeah.
set up slightly different.
so maybe we should go to the office first. Yeah, it's not
All right,
on the
so
board.
go ahead.
Okay, so this is the original proof where he was using the binary. And then basically, he's mapping like this countable infinite set to a set of all. And you just make it some random binary. The way you can prove that you can add it to the set after mapping all elements of the set of values, you just flip the first digit, the first number into a one. And then I drew it. I just try to.
remember looking at something.
Yeah,
But I cannot remember the context.
and then for base 10, the way that it works is just if you add one to each digit, but then if it's a 9, you go back to the
It roll back to 0.
Yeah.
So it's a congruent modulo 10.
Yeah.
Kind of that. Okay.
Yeah.
And but that works for basis 2 because it's just using the congruent modulo 2.
Right,
It's gonna-
exactly.
Yeah, so basically just roll over to the next step. Available digit to be that base.
Yeah.
So
Yep.
the way of thinking on this.
Okay, let's go to the office and then let's go back to the office. Don't argue with me. You can make a point, but you cannot argue. All right. So let's go to the office and then we'll talk about it in the office. Because the classroom, we're supposed to get out of the classroom after the class. So. And I need to borrow my key, Can I borrow your key again? All right.
Everything not into it. Yeah, I'm not trying to rely on curves, yeah.
Because when you're employed, there's no curve.
All right, so we're gonna I'll answer the questions in my office. Down. No, I dance. All right. So I don't know how you guys want to do this. You want to kind of ask questions at the same time, or do you want to go one by one?
Shouldn't be too long anyway. Mine is
Okay.
like a simple question, so. So continuing off of that problem, we know like with every case. Zero, we negate that to one, making the whole statement true.
Yep.
Now, in that case, we actually use the mechanics of the implication, right?
We always use the mechanic of
So that's where,
implication.
good, so that's where I get to this question right here.
Okay.
With member number 5, part 4.
Part 4.
Yeah,
Okay.
number of
So
question
part
5.
4 is not equal to, right?
Yeah, so
Yeah.
that was when S doesn't equal. So here you said since we were using a universal quantifier, I checked for a case where S does not equal U. I believe I found a case where S did equal U. So let me see.
But when S does equal to U, then S does not equal to U is false, which means the implication is true.
S is not equal to U is false, which means the implication is true. Exactly. Making it to where the whole thing would be true. Right?
No, it means one of the things you're ANDing is true, doesn't mean
Yeah.
the entire AND is true.
Yeah, because we're just checking one case, right?
That would be one specific case, yes.
Yeah. Right.
So let's take a look at how F looks, what F looks like. So F is this, right?
Yeah,
So
J is
that means if S is J, U is C, T is J, V is J, then part 4 would return false.
Yeah.
So since this is in a big conjunction because of this for all, this entire thing is false. But this entire thing is also just one of the items of the conjunction because of this for all. So the entire thing is false.
Yeah, that makes sense. I might have to just rework it real quick just so I can see exactly what we're talking about because I'm not actually seeing a case where S equals to U on here. C, no, J, no, B. So every case where S does not equal U is true. And we know that because we're looking at the tuples. But on the right case, T is not equal to B. We know that J equals to J. So we know that.
So you can make the left-hand side true, but the right-hand side false, which makes the implication false.
Right, left-hand side is true, which makes the left-hand side false, which is 0.
No, the left-hand side is true, but you found a case where the left-hand side is true, but the right-hand side is false, and
Yeah.
therefore the implication itself is false.
Yeah, but here's my thing. Like here, we know that every left case when we check B with each other, that this is true, which means that this
Okay,
negates
are you looking at the not equal to being true, or are you looking at the whole implication being true?
just this left side. S does not equal U,
Okay,
right? So we know that like, and maybe I'm just like overthinking, but we got every case B, J, and C where they just do not. Well, no, actually, B equals B, making this statement false.
false, but that's not important because it makes the implication true. So
True. And
Then we don't care what is on the right-hand side.
yeah, and then when we check the right hand side, we know that this statement is also false.
Okay, so do this. Make a list of 9 items
Yeah,
where you say, okay, which tuple is matched which two tuple, and then for each of the 9 cases, evaluate that condition.
yeah,
Because
Yeah,
that
but
way, that way it'll be clear to you why the universally quantified expression is false.
yeah, because that means every case has to be like S does not equal U, T does not equal V. Like every
No,
case.
go through that.
Yeah.
Really go through those 9 cases. 9
Yeah.
is not too much.
Yeah, no, I'm gonna do it, but I'm just saying like
Because once you go through that exercise, then you'll find out, oh, so that's what it is like to have a nested universally quantified expression.
yeah, but basically I'm saying like that means like the universal quantifier is judging whether every case
It's true.
satisfies that.
Have to be true.
Yeah, and if
If
there's
you want
one thing that doesn't satisfy, then the whole thing's false. In this case.
That is
Okay,
correct.
that makes sense.
Okay.
Yeah,
Okay.
that actually makes a lot more sense.
Okay. Well, that's good.
Yeah,
It's
I'm
good.
gonna-
See, it's really good that you
Yeah.
worked on this first, so that when we talk about this today,
Yeah,
it sinks in better.
yeah.
Yeah.
I just keep like so I take a minute to not think about it and I think about it again and I keep getting back to that like
Mm-hmm.
no like good zone where I'm thinking, oh man, why is it like this? And then I have to keep reminding myself, okay, it's because every case has to match.
Yep.
Yeah. So that's why you said it's good to just test every single case and then judge.
At least do it once or twice, just so that you can see how it works out when you look at all the details. Now,
Yeah.
once you get used to the whole concept, you don't have to look at every single case because you
Yeah.
already know what to look for. But
Yeah.
when you're just starting to get familiarized with the quantifiers, it really helps to look at every single case. It's like,
Yeah.
aha, I found one that is false. Okay,
That
so
makes
the whole thing is false.
Yeah.
Yeah.
Okay. Cool.
Okay.
All right, I'm gonna work through it. I'll let these guys
Okay.
ask their question.
All right.
I just had a quick clarification. In
Mhm.
reading the problems, I was understanding them a different way, but going over them in class, I realized like, because I got stuck on some parts and
Okay.
then I got a realization in class. So I was making, truth tables. Because what I did is I broke it down into like a formula like this, seeing the implication. Kind of like rewriting this into this.
Okay, I see that. Okay, you can do that.
And I found like when it's false, and I was like trying to figure out all cases like when it could be false.
Yes.
And since there's none possible, then it has to be true.
Mhm,
The
mhm.
problem I ran into was with number 3. Is because like I found like 3 possibilities when it could be false. But then I'm thinking of edge cases of when it could be false of stuff that's not in set X. Or no, everything has to be in set X, but I mean for here, for it to be in the function, I was thinking of tuples that could be outside of it since there's false here. Because I was just thinking of truth table wise, but that's not what we're doing.
So in this case, this is more like a filter. In other words,
Yeah.
there are a bazillion, two tuples out there in the world, but the 2 tuples that do not belong to F, I don't even want to consider.
Yeah, so for when we have like the AE in X or here,
Mhm.
kind of like when they're next to each other type thing. That's more like when this is next to each other, that's more like a rule that we're following for the question.
It's more like both are filters. So this one is a filter that says, there are a bazillion things in the entire world, but we only care about the things in X.
Okay,
And this one says, there's a bazillion things in the whole world, but we only care about elements of F.
okay,
So by the time you get to E equals to U, basically we're only looking at E being as an element of X and U being a first item of a 2 tuple of F.
got you.
And we are basically restricting what we are really focusing on because everything else we don't care.
And for like with A, all the possibilities like that we find, like they have to be true. And for E, only one of the possibilities need to be true.
That is correct.
Okay,
So the for all is basically a gigantic conjunction, and then the there exists is a gigantic disjunction. So
okay,
now you have a disjunction, you have disjunctions embedded in